Now, obviously, if we're going to try to look at analogous areas in human beings, we can't necessarily go in and stimulate a bunch of cells. But what we can actually do that is certainly less invasive than stimulating preferred orientations of motion like we do with monkeys is by looking at motion after effects. So I know that when we talked about color, we talked quite a bit about after images. Well, it turns out that motions also have after effects. So one of the examples that I gave earlier in the semester, I showed you a YouTube video of a spiral that I asked you to watch for a little while, and then I asked you to take a look in your hand. And what will often happen with a motion after effect, you get an illusion of motion in a stationary object after you've been looking at it for a while. And so let's kind of take a look at some of these different aspects. So again, we're going to go to our favorite thing today. So we are going to look at motion after effects. All right, where you at? Here we go. So we are looking at motion after effects here. So in this particular case, and I would highly encourage you to check out this companion site because this one in particular is a lot of fun, and I may not spend as much time on it as you might potentially want. So I'm going to go ahead and I'm going to click on one of these arrows, and we can change the speed if we want. At some point it will either go to medium speed, slow speed, or fast speed. But I'm going to go ahead and click this so that we see these dots moving up. I'm going to go ahead and make that kind of fast. Sorry if that's a bit overwhelming. And I'd like you to try to look at this fixation cross, this white cross in the center of the screen for just a few seconds. 3, 4, 5, 6, 7, 8, 9, 10. I'm going to click stop. Is anybody else kind of seeing those dots almost slowly move downward a little bit? It's very, very subtle, but it kind of looks like they're drifting in the opposite direction that they were originally heading in. Sometimes I actually get this experience driving in my car. If I spend a lot of time constantly moving forward and then I stop at a stoplight, I almost get the visual sensation that I'm moving backward. And so this is what a motion after effect is. Now, what's especially cool about this is this does actually show that we do have an opponent process for motion. If you look at something going in a particular motion of direction for some time, so for example, moving to the right, and then that motion stops, you're going to get the sensation of apparent motion, a slight drifting motion towards the left. So it's kind of an opponent process. Now, what's especially cool about motion after effects is that you can have what is called interocular transfer. So before I tell you about the significance of this, we're going to go ahead and try this again with interocular transfer. So what I'd like you to do is cover your left eye or close your left eye as I play this video. And then once I stop, we're going to do that again. So we're going to do what we did before, but then I want you to open your left eye and close your right eye. And so what should happen is that motion after effect should transfer to the other eye. So let's go ahead and give this a shot. So go ahead and close your left eye now, and I'll start playing the video. So we've got that nice upward motion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I do get a little bit of downward motion there when I switched eyes. So what's kind of cool, and I would encourage you again, go to this site, check it out. It's a lot of fun to play around with these things. But what this kind of shows us, so I was watching that with only my right or only my, I was watching that only with my right eye. I had my left eye closed. But then I switched so that I closed my right eye and I opened my left, and I still got a little bit of a motion after effect. So what this means is that motion after effects are going to occur in cells that process information from both eyes. So this is really important. So this means that the effect is basically getting information from both eyes. So what's kind of cool is that you don't necessarily, that because it's operating on both eyes, you don't necessarily have to have both eyes open for this to happen. You can actually transfer that information from one eye to the other. And it's because of adaptations in middle temporal area that actually causes this. Very cool. Now, there are two major different types of motion. The most of the motion that we've been talking about so far is what is considered first-ordered motion. So we're looking at changes in positions of what we would call luminance-defined objects. So we're actually looking at objects, they change position, and we notice changes in position because of those changes in luminance. Now, on the other hand, if we're looking at something called second-order motion, we're not actually we're noticing motion, but it's not because of any necessary change in object position. Rather, we see motion because we see changes in texture or contrast, but we're not necessarily getting a change in luminance. So, I'm going to show you, again, we're going to hop on our companion site. I'm going to show you some stereograms of random dots, kind of like what we've been looking at for the last couple of chapters. And what you're going to see is an instance of second order motion. So we're going to go back. We're going to go to different types of motion. So we're going to look at our second order motion. So go ahead and take a look at this image. So you can kind of see an appearance of motion, stripes moving over to the left. But here's kind of how this works. Now, there's no changes in luminance here. This is a change in texture, but not a change in brightness or lighting or anything like that. So here is a very small section of the surface. Now, here is that same section, but all of the pixels have been reversed. So all of the white pixels you see here are going to be black. All of the black pixels are going to be white. So here's what's kind of interesting. So the only thing that's changing here is the pixels. These are areas of reversal. So here's how they actually created this second order motion. So basically what they did, they basically passed these moving bars through this this stereogram so that dots that are covered by white bars are inverted, dots that are covered by black bars are not. And this is second order motion because there aren't any objects to track here. There is not a change in luminance here. This is just a change through texture or contrast. And that's what creates that positional change. So now, how do we use visual information to help us navigate our world? So we use motion. So we are constantly traveling throughout the world, and either we are moving through the environment or other objects are moving through our environment. And so if you've had me for cognitive psychology, some of this might sound a little bit familiar to you. For those of you who have not had cognitive, don't worry, I'm going to talk about this quite a bit. So this is J.J. Gibson's theory of direct perception. And Gibson believed that the goal of perception was largely to act upon objects in the world. So that's why you are able to perceive things, so that you can actually interact with them and act upon them. And so Gibson believed that when we are moving through the environment, we utilize what he termed an optic array. An optic array is basically a pattern of light that falls on the retina, and this array has a particular structure, and it contains all of the visual information from the environment. Now, one of the things that is a little bit odder about Gibson's theory of direct perception is that he believed that through a quality called resonance, that we actually tuned in to the array like we were dealing with a radio to obtain visual perception. And so one of the things that we find is that as we move through the environment, we have what Gibson termed optic flow. So basically, imagine that you're kind of moving through the environment, and let's say that this center point is the focus that you are heading toward. This is the part of the visual field that you are heading towards. As you move through your environment and you move closer to this central focus, it's going to seem as if things in the environment radiate outward from that point. So this point, by the way, is what Gibson termed the focus of expansion. It is from this center point that you are heading from that all of the information in the environment radiates outward. So to kind of give you an example of what this looks like, here is an example of optic flow. So what you're looking at here is a display of random dots. This is kind of like it kind of looks like the ground, and we're kind of focusing on this pole. So this is what the image looks like. Here's what would happen if we are moving forward. So notice that what happens is that as we move forward, let's say that this is our this is the direction we're heading in. This is our focus of expansion. Notice that everything kind of moves outward toward the field of view. So when everything's kind of radiating outward, that indicates that we're moving forward. Now, on the other hand, if we move backwards, everything seems to radiate inward from that point. And so this focus of expansion, you can see it's kind of in the center of this movie. That helps us figure out the direction that we are going in. So here's kind of another example of this. So imagine that you were actually trying to land a plane, and if you know anything about Gibson, this actually makes a lot of sense because Gibson's work was done largely on pilots and things like that. So let's imagine that we're trying to land this plane. Here's our runway, here's a hangar or a tarmac, and so here is our focus of expansion. We basically want to land here. That is the direction that we're heading in. And what's really critical here is that our focus of expansion ultimately stays motionless. The rest of the visual field is going to move outward from that point, provided that we're moving forward. Additionally, the farther away that something is from the focus, the faster it appears to move. So notice that things that are a little bit closer to the focus, they move very, very slowly. Things that are farther away from the focus, like this part of the field, are going to move much more quickly. So generally, distant information is going to exit the visual field and new information is going to radiate out from that focus. Now, whenever you change direction, your focus of expansion will change as well. And the focus of expansion and our optic flow field provides us with a lot of information about things like our direction, how fast we're going. So if we are moving very slowly, items are going to radiate more slowly from the focus of expansion. If we're going more quickly, that optic flow is going to change a lot more. And it can also tell us information about our altitude. Now let's talk a little bit about biological motion. So perceiving motion in other people. So we're actually pretty good at detecting biological motion. And we're actually really good at this even when our viewing conditions are quite poor. So here's a case of biological motion. So here's image 1. And it's kind of hard to see. Here's image 2. And if I flip those back and forth, you might get the sense that somebody was actually walking. But when you put them together very quickly, it creates a smoother sense from these point light displays. So these are just different lights or different points that have been animated, but put together, they create the sense that a person is walking. And generally, let's say we try to reverse that image. It definitely looks like it's walking backwards, but it doesn't feel as smooth and as natural as this does. So even when viewing conditions are poor, even when we're only looking at little dots, it's very, very easy for us to perceive that motion. So we do this with those point light displays. And it turns out that we can actually perceive human movement with as few as 6 lights, even when that film is short. Interestingly enough, too, we can even identify the reported gender, my apologies for putting sex on the slides, I mean gender, of the actor. And this is partially because men and women do move somewhat differently. Men tend to walk more through their shoulders, so their shoulders tend to move a lot more. Women tend to have a little bit more of a hip sway, and that's largely because women do tend to have wider hips than men do. And so because of that, they have a little bit of horizontal sway that men really don't have. So men tend to lead from their shoulders. Women tend to lead a little bit more from their hips. And that's something that you can also detect with small point light display. Yeah. So here we go. So what kind of things do you see in this point light display that I'm about to play for you? Okay. So hopefully you see somebody walking towards you. Here you see somebody jumping. Here you see somebody climbing up some stairs. Now they're climbing down some stairs. What is happening here? Ah, somebody's sitting. What are they doing here? They look like they're stretching or doing something with their hands. So in this particular case, it's really easy to perceive that motion. Now, let's talk a little bit about detecting objects in motion as well. So this is a case where, unfortunately, this is a terrifying image, somebody actually being hit in the face with a baseball bat. So this is what is known as time to contact, or TTC. So generally, we are moving through our environment, and sometimes objects in our environment are moving towards us. So how do we figure out how quickly an object is moving towards us? Well, what we could do, we could kind of take the physics approach of things. We could do this based on, we could focus on how far away the object is and figure out the speed of how it's moving. We could do this. We probably don't, because that would take a lot of time. And at that point, the object has probably already come towards you. What we do instead is something that is very simply referred to as tau. So basically what we do when we're figuring out how quickly an object is coming towards us, we focus on the size of the retinal image and the rate of its expansion. So the idea is that as an object comes closer to us, it will get larger upon our retina. And if we can calculate that rate of expansion, we can figure out how quickly it's coming towards us. Now, here's what's really critical. Tau assumes that object velocity is constant. There's no sudden rapid accelerations or decelerations. This assumes constant velocity. So this may not work very well if you're trying to figure out how close the car in front of you is stopping so that you can brake appropriately. Tau may not work as well for sudden accelerations or decelerations. Now, obviously, here are some big problems in tau. Object velocity often accelerates. Gravity is a very good example. Falling objects will tend to accelerate due to gravity. Tau is often based on time to contact with the eyes. So this doesn't really work very well if we're talking about contact with other parts of the body, or heaven forbid, if we're dealing with a vehicle. It really only works for objects that are symmetrical spheres. And here's what's really critical. The changes in the image and its rate of expansion must be noticeable. So let's consider tau. So when people are actually given balls that are rapidly accelerating or decelerating, one of the things that's kind of interesting is that people tend to find that if an object is rapidly accelerating, they will often overestimate the time they have to catch it, because tau assumes constant velocity. So if an object suddenly accelerates, we tend to overestimate it. On the other hand, if the ball is decelerating, we tend to underestimate how much time we have. So oftentimes, if we're assuming a constant velocity, we are going to probably miscalculate if something is rapidly accelerating or decelerating. Additionally, if we can change the rate of expansion by getting balls to deflate, that means that the ball will have a lower rate of expansion. And we do actually find that, consistent with tau, participants take longer to grab these balls. So what this kind of tells us is that we do use tau, but it only works under a very limited set of circumstances. Now, what about vertical drops? Now, you would think that because of acceleration due to gravity, typically tau would predict that people aren't very good at this. But it turns out that observers are much better catching them than tau would predict. So what this tells us is that while we do use tau, we do also understand that objects accelerate due to gravity, and we adjust accordingly. Additionally, our understanding of how objects change size through binocular disparity and familiar size also influence us. So tau is not the only thing that we have. So I'm going to go ahead and stop here. Next time, we will focus on eye movements and saccades.